Hi everyone, and yes, persistent memory again. So today we are going to talk about some of our works and experience on the persistent memory, and especially how to leverage the persistent memory on the cloud environment to speed up the Spark application and make it more elastic. And before the talk, please allow us to do a quick introduction about ourselves and our company. My name is Shao, and I am an expert software engineer in Tencent Cloud. And I have been working on open source big data areas for many years, and I'm a Spark committer and a Navy PMC member. And here's my co-presenter, Peiyu.
Yeah, my name is Zhuang Peiyu, so I'm coming from MemVerge. I'm a software engineer in MemVerge.
Mm-hmm. So my company is Tencent Cloud. Tencent Cloud is the second largest public provider in China, public cloud provider in China. It has a largest big data cluster with more than 12,000 nodes. And in every day, it will generate more than 3 trillion of array codes, and with a computation of more than 3.5 trillion of computations. And the vision of the Tencent Cloud is to connect data, tech, model, and scenario together. And here is a product matrix of the Tencent Cloud Big Data and AI. We provide various products from the infrastructure to the specific scenarios, from SaaS to PaaS, to provide user an ability to build their own AI and big data workload out of box.
And about MemVerge, MemVerge is a startup company based in San Jose, and we started in 2017. So we are delivering the world's first memory converged infrastructure, which is called MCI. And our system is called Distributed Memory Objects, DMO. We are trying to deliver a system with total up to 768 terabytes capacity, and per node, we are targeting 72 gigabytes per second bandwidth for read, and we're targeting lower than 1 microsecond access latency.
Mm-hmm. So now let's go back to the date when MapReduce just came out. So why MapReduce became so popular at that time? And I think the one advantage of the MapReduce set is that it can run on a commodity cluster without any spatial hardware. So a typical commodity cluster looks just like this. So we have several nodes with CPU, memory, and disks. Nodes are connected with a switch to combine as a cluster. A typical bandwidth of the switch at that time is about 1 GB per second. So with such hardware, how did we design a data application? The first thing we should consider is to balance the network bandwidth with disk throughput. At that time, the network bandwidth is quite smaller than the local disk throughputs, assuming that we have several disks in one node. So moving the data on the wire is quite expensive. So one optimization in the application design is to moving the code rather than moving the data. So this is also called data locality, which is still quite important nowadays in tuning the MapReduce-like application. Another thing we should consider is about the fast small memory versus slow but large disks. And memory, though very fast, the size is quite limited. So when we processing a large amount of data, it is unavoidable to spill the data to the disks. So how to mitigate or how to fully gain the performance of the disks? And one optimization is to change the I/O access pattern, and usually change from the random access to the sequential read and write, so that we can get best performance of the HDDs. But within this decade, the hardware has changed a lot. According to the chart provided by the Cisco in the left side, here is a data center bandwidth migration. And from the year 2010 to the year 2019, the bandwidth of the network is increased from the 1 GB per second to 10 GB, even up to 40 GB. Now a fast network bandwidth can be reached up to 100 GB per second. Also for the storage in data center, as shown in the right side of the chart, in the right side, this is the data coming from Seagate, shows that from year to year, the occupation ratio of the SSD is increased, and HDD is not the only choice in the data center storage. So using a tiered storage using different kind of storage can mitigate the gap between the memory and disk. So the changes of the hardware significantly affect the data center, especially the cloud architecture. And now, what happens changing to a modern cloud data center architecture? The one change is that separation of data and computation. Because of high-speed network between the compute node and the storage box, so we can get a equal performance with a remote storage compared to the local disks, because the network bandwidth is much higher than the local disks. The second change is that we can use tiered storage for hot and cold data, because now HDD is not the only option in the data center storage. So we can use the various kind of SSDs to mitigate the gaps between memory and HDD. And again, let's image the storage hierarchy in the data center, memory and storage. Here is a pyramid of the storage in the data center. On the bottom of the pyramid is the HDD, which provide the largest size, but the speed is the lowest. So it is quite suitable to store the cold data. And in the middle of the pyramid is the SSD, which has a balanced capacity and performance. And on the top of the pyramid is the DRAM, in which the size is quite limited, but can get a higher speed. So it is suitable to store the hot data. So let's think about one question: do we still have the room for the new hardware which can add it into this pyramid? For example, the one hardware that can get a better performance compared to SSD, and also get a better capacity compared to DRAM? The answer is yes. And I think the previous session already talked a lot about DCPMM. And this is a new hardware, persistent memory hardware, just announced this year by Intel. And this DCPMM has a low latency and a high throughput like DRAM. And its latency can be reached to about 200 to 400 nanoseconds. And the bandwidth can be reached to about 8 GB per second for read and 3 GB per second for write. Also, it has high density and non-volatility like NAND. So each server can be equipped up to 6 TBs. And so with such characteristics of the DCPMM, it is quite suitable to build a memory speed storage system. So here comes a question again. So how do we leverage the DCPMM, especially in the cloud environment? And one option is to add this new hardware to each node, so that the application running on each node can be leverage the advantages of the DCPMM. This is a very straightforward option and can get a better performance. But the problem is that in a data center architecture, in an existing data center, and because of this new hardware requires new CPU and a new motherboard, but all the hardwares are already existed. So it is hard for the existing cluster to leverage this new hardware, and unless we renew all the machines in the data center, and that's a problem because only the newly provisioned cluster can be benefit from this new hardware. So here comes another option. We can use a DCPMM with high-speed network to build a very fast memory-based storage system. And using this storage system as a distributed remote storage to be used by existing cluster, so that the existing cluster can leverage from this remote storage without needing to add any change to the hardwares. So this second choice is a more practical choice for the existing data center and cloud environment. So here we are choosing this second option as a second option to build an elastic Spark solution. As you can see here, in the left side is the existing Spark cluster, and on the right side is the Spark accelerators, which are equipped with persistent memory. And these two clusters are connected with a high-speed network switch. So existing Spark cluster can use the remote Spark accelerator to read the source data. Also can cache the intermediate data like RDD caching or storage, and also could store the temporary shuffle data on this remote storage, and by leveraging the persistent memory. So here we build a persistent memory centric data platform. On the bottom of the platform is the hardware, is a cluster which equipped with shared persistent memory, and we also build a distributed memory objects storage system, which is called a DMO. This is used as a distributed object system, and on the top we also build an adapter which can be communicated with Spark application and the DMO. This as a whole is a persistent memory centric data platform. And in this when integrated into the Spark, we choose three typical scenarios. One scenario is to use the persistent memory and the DMO as a data source, and we build a Hadoop compatible file system API on top of this DMO system, so that Spark could directly read data from this DMO without needing to do any code changes. And second, for the RDD or data frame caching, we also add a extra persistent level or persistent APIs in the Spark code, so that the intermediate RDD data or the data frame table can be cached on the DMO system. And finally, we also build a remote shuffle system on top of this DMO, and which is used to store and exchange shuffle data remotely. This is quite useful in the cloud environment, because in the cloud environment, typically the computation and the data is separated, and the local disk is quite limited. So this is very suitable for the cloud environment. Now I will hand over to my co-presenter Peiyu to give us a deeper introduction about this persistent memory equipped remote shuffle service.
Okay, thanks, Saisai. I will talk a little bit details about how we equip the shuffle service with the persistent memory. So firstly, let me briefly talk about the current architecture of the shuffle manager. So as we all know, that the shuffle manager lives in the Spark executor. And the shuffle manager, for I/O, the shuffle manager will talk to the block manager as well as the local file systems. For the block manager, it mainly stores the shuffle data. And for the local disk, the shuffle manager will persist the shuffle index file as well as the spill files. So this architecture causes some problems. One of them is that this shuffle manager contains the logic of the shuffle algorithm as well as the logic to persist the data and the network. It's make us hard to switch the network or the storage under this shuffle manager. And our solution, okay, there are several problems of this current shuffle algorithm, shuffle implementation. Well, one of them is the pool elasticity. So by talking about pool elasticity, I mean because the block manager lives with the executor, that means if your executor dies, you lose all the reference of the data on that executor's block manager. And any data in that block manager has to be recomputed. If you are running this shuffle service, if you are deploying the shuffle service, you will find out that actually the shuffle service is still persistent the data in the computer node. That means if you lose the computer node, you still lose part of the shuffle data. And in the later session, you have to recompute all those lost shuffle data. This is the problem caused by about the elasticity. And another thing about this is that it causes some heavy overhead to the node manager. That is also because that your shuffle manager or your shuffle service is coexisting with the node manager. And it will bring heavy overhead for the node manager if you have heavy shuffle tasks. The third one is that this architecture is not suitable for the cloud environment. So by talking about cloud environment, in a typical cloud environment, we are trying to separate the computing resources from the storage resources. So the point of this is that the cloud user needs to scale up when they need more computing resources, and they want to scale down when they want to save the cost. But if you are saving the if you are saving the shuffle data in the computer node, that makes your computer node stateful, and it's hard for you to scale down because whenever you try to scale down, you result in a recompute of the shuffle data. Okay, and the community has already realized these problems, and also they have filed several issues to track these problems. We can see that we list those issues here, and if you are interested, you can see some related discussions in these issues. So here comes our solution. So in MemVerge, we developed our own Splash Shuffle Manager. The key difference of this Splash Shuffle Manager is that it extracts an storage interface from the original shuffle algorithm. So that means we barely keep the shuffle algorithm untouched, and then we separate all those I/O requests into a separate interface. This project is now open source and it's available in the github.com. So this is a very simplified diagram of how we deployed our shuffle manager in the Spark environment. So say our Splash Shuffle Manager, just like the original vanilla Shuffle Manager, it still lives with the executor. The difference is that, as I just said, it talks to the storage plugins interface instead of talking to the local system or talking to the block manager directly. So in the storage plugin, you can have different implementations. You can have implementations for NFS, for local file system, for HDFS, for S3, or in our occasion, it's the DMO implementation. So by separating the storage from the shuffle algorithm, we can separate the storage from the computing. That means we can make the computer node fully stateless. And when the computer node becomes stateless, that means we can dynamically remove the executor. We can dynamically remove the computer node without the cost of recompute all those shuffle data. And what's more, as you may notice that the shuffle manager's configuration and as well as the plugins configuration are the per application configuration that you can specify. I mean, you can specify these configurations for each application. That means you can specify different storage or strategies for different Spark applications. So if you are having an application with very high computing resource demands, you can just use the vanilla shuffle manager implementation. If you are having an application with large shuffle data but lower computing resource, you can export the shuffle data into a HDFS system. And if you are having an application with higher computing resource and as well as higher shuffle resource, you may try to switch to faster storage systems. Okay, so in our storage plugin implementation, we connected the shuffle data into our demo system. And our demo system, as I just mentioned, is a distributed file system based on persistent memory. What we're trying to do is to utilize the fast feature, the characteristics of this new media. And the storage plugin also allows us to switch the network protocols that was used to transfer all those shuffle data. For example, when we switch to the demo system, we can dynamically configure the network protocols used between the computer nodes. Like we can transfer those shuffle data in RDMA or in DPDK in order to speed up the shuffle efficiency of the whole cluster. And this configuration would be totally transparent to the upper Spark applications. Okay, in order to validate our solution, we did several benchmarks. So the first benchmark was run in bare metal machines. Here I list some of the configurations of our benchmarking environment. What we have in common is for computer node, 10 gigabyte Ethernet. The driver was on 4 gigabyte memories. The executor has 6 gigabyte memory. Totally, we have 160 cores, and each executor has 4 cores. For comparison, we have a baseline which has 4 HDD disks that was used for local disk shuffle. And our implementation is called DMO, has another storage cluster. They have 2 storage nodes, and each node were assigned 400 gigabyte of persistent memory. And the first benchmark is about TeraSort. So we generate 400 gigabytes of the TeraSort input and run this TeraSort application in both baseline and in our demo implementation. The y-axis is the duration of the job, is the duration in minutes to complete the TeraSort job. And the first bar is the baseline. The blue box represents the duration we spent in the map stage, and the purple box represents the duration we spent in the reduce stage. The second bar indicates the DMO with the UDP network, and the last bar represents the DMO with DPDK. We can see that, especially in the reduce stage, the DMO's implementation generate performance enhancement almost larger than 50%, and during the shuffle right stage, I mean the map stage, we also get some performance gains. Okay, and our second benchmark is about the TPC-DS. So TPC-DS, as you may know, is a bunch of queries that was used to analyze the system's performance about the SQL queries. And not all of them were shuffle-heavy queries. So because we only touched the shuffle part of the Spark, so we pick out those queries with heavy shuffles and list them here. So for comparisons, you can see the y-axis are the durations we spent for each query, and the x-axis are the IDs for each query. The blue bars are the baseline, and the purple bars are the DMO. For those shuffle-heavy queries, we can see that The DMO normally gets about 50% or 40% performance improvement for these queries. Okay, to further analyze the problem, we tested the we test those shuffle-heavy queries under different scale of data. So we pick 3 kinds of data size. They are the 400 gigabyte, 800 gigabyte, and 1.2 terabyte data size. And you can see from these 4 charts here demonstrate the result of 4 queries. Again, the left y-axis shows the durations used to complete each query, and the right y-axis shows the percentage of improvement compared to the baseline. You may discover that when the data size is small, like 400 gigabyte, our implementation may not be as efficient. It's on par with the vanilla Spark, but sometimes maybe not efficient as the original Spark implementation. The reason is that, as I just talked, the vanilla Spark has used the block manager to persist all the shuffle data. And when your executor has enough DRAM in the executor, it will try to put those shuffle data in the DRAM as much as possible. So if your DRAM is enough, that means all the data were in the DRAM, and we do not see much improvement here. But when you increase your input data size, and when the overhead of the local disk kicks in, we can see that an external storage cluster benefits much from this. And in the first queries, we can even see that when the data reaches 1.2 terabyte, we sometimes even get more than 60% performance gain compared to the baseline. Okay. So another environment we did with Tencent is that we try to deploy this solution in a cloud environment. So this is our cloud environment configuration for the benchmark. We have 4 Sparkling hosts, which is used as the computer cluster. And we have 3 DMO hosts, which is used as a separated storage cluster. The Spark configuration is almost the same with the previous one, except one is that we have much larger executor memory. For each executor, it's on 30 gigabytes of memories. The benchmark we choose is still TPC-DS, and the data size is 1 terabyte. We choose 10 queries with heavy shuffles. And as you can see here, this is the result for our benchmark in the Tencent Cloud. Basically, for those shuffle-heavy tasks, we gain about 10 to 15% performance gain. But in some situations, we may have some performance degradations. So that leads to the future work we are having now. So what we are trying to do in the future is that we are still trying to verify our implementation in a production environment, especially in a cloud environment. And in the shuffle manager's perspective point of view, we are still trying to enhance the data path performance of the Splash Shuffle Manager. And because for this Shuffle Manager, we have the ownership of the code, so we are trying, maybe we could add something to enhance the algorithm of the shuffle itself, like adding the map side merge in the Splash Shuffle Manager. And we are also trying to add the NIO style of Java NIO style IO interface in the Splash Shuffle Manager. The reason for this is that currently we are using the traditional input-output string style of interfaces, and this may not be as efficient as the NIO style interface for some storage systems. Okay. And the last but not least, we want to land this Splash Shuffle Manager in a real cloud environment.
Thank you, Peiyu. So as a summary, and persistent memory, it brings us a fundamental changes to all the data centers and enable a data-driven future. And MemVerge and Tencent Cloud will deliver the better scalability and performance on low cost, not just for Spark. We are also trying to enabling a persistent memory on AI, big data, and different kind of workloads and different kind of in different scenarios. And in last, and we should thank Intel to support our works, because this hardware is supported by Intel. So that's all. Thank you.
Okay, any question?
Yeah, I have a question. Good talk. My question is like, for the performance comparison in the cloud, they look like almost the same, and sometimes the improvement is not so obvious, right? From the
Yes.
For the last, I think yes.
This one.
Is this because the 10G network stuff?
Yes, yes.
What's the major reason like you get a graph like this? Yeah.
Okay, so we are still trying to root cause the problems of this performance outcome. So from outside, the major concern is that because, as I just mentioned, we are choosing deployment of separating the computer node and the storage node. That means the network may become a bottleneck when you communicate all those shuffle data into the to the cluster node, to the storage node. This is one part. And another part is that, as I just mentioned, I think the data paths in the Java side, mainly in our shuffle manager side, still needs the room for tuning, and as well as our performance tuning are still happening in the persistent memory side.
Let me add something more. And as you can see, here is a benchmark from the lab environment, and the performance is much better. And here is this is a result from the cloud environment, so it is quite close. The problem, what I can say now is that the cloud environment is much complex compared to the lab environment, especially for the network isolation. Because first thing is that the cloud environment, we provide a VM virtual machine on top of the physical machine. So that's the difference. Second thing is the network isolation, because the network is shared between the virtual machine. So there's some problem of the network competition. And also, we don't know the physical layout of the virtual machine, because it may be co-located in one node, or it may be separated in different nodes or different racks. So the performance is not so controllable compared to the lab environment.
Okay, any other question? Okay, I think that's all for our presentation. Thank you for coming.
Thank you.